Hi there. I bet you know metals and nonmetals join through ionic bonding. Therefore, if we had the metal sodium and the nonmetal chlorine, these two atoms would have been said to join ionically or through ionic bonding. If we had carbon and oxygen, that would be called covalent bonding. Now, how will a metal sodium join with another sodium atom? This is Z Online School, and welcome to our lesson where we'll be looking at metallic bonding. By the end of this video, you're going to know these things. You're going to know how to define metallic bonding, how to represent metallic bonds, the properties of metals, and at the end of this video, we've got a bonus tip for you to be able to answer questions involving metals better. Let's define metallic bonding before we get to do anything else. Metallic bonding is the bonding of metals through the force of attraction between metal ions and free electrons. In all kinds of bonding, that's ionic bonding and covalent bonding inclusive, ions are always involved. In ionic bonding, there's a transfer of ions. In covalent bonding, there's a sharing of ions. But in metallic bonding, there's a force of attraction between free electrons and metallic ions. Now, it's good to know where this force of attraction comes from. I'll try my best to keep this in the simplest terms. Let's say we have a metal ion here and another metal ion here. The force of attraction comes about because in a metal we've got electrons all around these metal ions. Therefore, these electrons want to go back to these metal ions. However, there will be many metal ions that will be attracting this electron. So, these electrons and the metal ions will just have that force of attraction between them. The metal ions won't be able to fully attract the electrons back into their shells, but they'll be just held together because of this attraction. That's how the force of attraction comes about. How can we show metallic bonding diagrammatically? You know, we can show ionic bonding in diagrams, covalent bonding in diagrams, but how do we show metallic bonding? Metallic bonding is easily represented. You just get a rectangle, then inside it you draw some circles with a plus sign in them showing those are your metal ions. Then after I finish drawing those metal ions, then you start adding your electrons. Your electrons will just fill those spaces you have around. And when you're done, you've represented metallic bonding. Under metallic bonding, you should get to know that this group of electrons will be referred to as a sea of electrons. You should also know that this group of metal ions here forming a regular shape will be sometimes referred to as a lattice. With that said and done, let's look at the properties of metals. There are 6 properties of metals that you should be able to remember. The first, as you can see, is the property of a metal being lustrous. This just means a metal has the property of being shiny. Most metals will be shiny. However, sometimes their shininess might not be very pronounced because they are not polished all the time, but most of them are shiny. You should always remember that the most lustrous metal is rhodium. In this diagram, the left part of this ring doesn't have any rhodium, while the right part has a rhodium plating. You can see the differences in how shiny the right part is. Metals are also known to be sonorous, meaning they produce a sound when they are struck. To remember this, think of a bell. Bells were a common thing some time back, but now I think most people use sirens. The most sonorous metal known is silver, and I guess this is why most bicycle bells are made with a very shiny metal, which I think might be silver. Another property of metals is them being ductile. To be ductile just simply means the property of a metal to be drawn into thin wires. Let's say we had this machine, which is a wire making machine, and inside it we inserted a metal which we wanted to convert from a big wire to a smaller one. we exerted some force that this metal started going forward. What happens is a thin wire will be produced at the other end. This will only happen because metals are ductile. They can be drawn into thin wires without any breakage. The most ductile metal is copper. If you want to see this, try to get your charger. Just hope it doesn't work. Cut it and you'll see some copper wires inside the charger. Metals are malleable. To be malleable simply means a metal can be hammered into different shapes without it breaking apart. It's very easy to confuse ductility and malleability, but you should be able to note the difference. Ductility is that metal being drawn into thin wires, while malleability is a metal being hammered into different shapes or being bent without cracking. In this photo, we see a blacksmith hammering a metal that has been heated. These metals are just heated so that it can be faster to bend them. However, they could be bent even without heating them. The most malleable metal is gold. I guess this is why some time back it was used to make money, coins, and all that. This time it's used in electronics, medical equipment, and a lot of things. Gold has the property of not wearing out. Metals have got a high melting point, meaning a metal will need you to raise the temperature so high for it to be changed from a solid to a liquid. In this picture, we see a metal that has reached melting point. You can see the metal is liquid and it's very light in color. You can see it looks whitish, reddish. That color shows the temperature is very high. I'm sure you've seen something that's hot, maybe charcoal, a hot plate on the stove. You see it shows a reddish color. So reddish color usually shows something is hot. In this picture, you can see the metal being poured out of this pot is very hot. To melt a metal, you need a very high melting point. This is because for you to break those forces of attraction between the metal ion and the electron, you need a lot of energy. So in this picture, it means that attraction has been broken. Tungsten has got the highest melting point. Of all metals, it's the metal that requires you to heat it so much for it to melt. This is why tungsten might be used to heat other metals like the one we see in the diagram. Apart from that, tungsten might be used in cutting tools and even light bulbs. So generally, in places where we experience high temperatures. Last but not the least, metals are good electrical conductors. In this picture, you can see overhead cables. I'm sure you see one of these every day, as electricity is one of those things we are getting used to. In this era, we even have electric cars. Metals are good electrical conductors, meaning they are able to conduct electricity. They don't stop electricity from passing through them. This is why when you touch an electric source with a metal, you get electrocuted and maybe even die. Please don't try that. The best electrical conductor is silver. However, silver won't be used because it's quite expensive to make into cables. Therefore, people result in using copper. Now, I'm sure you've noticed we've got quite a number of properties to remember, right? Today, I want to share with you a way you can remember each of these 6 properties. You won't need to be a genius to remember this, but they're just 2 words that you can use to remember these 6 properties of metals. The first word is malleable, and the second, as you have seen, is shield. It's quite an easy way in which you can remember these 6 properties. Malleable is that property of the metal being able to be hammered into different shapes without cracking. Then S is for sonorous, HI is for high melting point, E is for electrical conductivity, or simply metals are good electrical conductors. L is for metals being lustrous, meaning them being shiny, and D is for metals being ductile. Thanks for reaching till the end of this video. Now, look out in your community or your environment and see if you can identify any metals using these properties.